Hey everyone, and welcome back to this class, the Numpy stack in Python. In this lecture, we are going to do an example of classification in code using all the functions we just talked about. Now, I'm not going to be typing everything here character by character, since in this lecture, what I have to say is more important. So I'm going to focus on explaining what the code is rather than just typing. However, you are encouraged to do the typing since you are the one who has to learn this API. Don't just copy and paste this code yourself. Also, don't equate my speed to your speed, and don't equate the speed of the video as the speed you should go when you're trying to understand this stuff. Also, please remember that you can try this code out wherever you want. Whether you like Jupyter Notebook, or you like plain text editors, or you like command line editors like Vim, it does not matter. Remember, Python code is Python code, no matter the environment. Let's get started. The relevant file for this lecture is classification example.py. So first, let's import Numpy since we'll need it later. Next, let's import our data. So scikit-learn comes with some datasets that are readily available for you to use. One such example of this is the breast cancer dataset. And so this lets us highlight yet another important application of machine learning classification, and that is diagnosis of disease. These days, there have been instances where machine learning algorithms have learned to correctly identify disease on par with or better than human experts. This is great because human experts are not scalable, whereas machine learning algorithms are just code that we can replicate much more easily. Alright, so let's copy and paste this. And so what we just imported is actually just a function. So we need to call this function in order to get the data. So let's do that. Now we don't actually know what's just been returned, but we can check what it is by printing the type of the data or just printing the data itself. I recommend doing both. So let's print the type. Okay, we see that this is a bunch object. Now you probably don't know what that is, but you can check its attributes just by typing data and then pressing dot and then hitting the tab key. So here I can scroll through all the attributes and instance methods of this object. Now this might not be obvious at first, so you might have to just take my word for it. But this data object behaves a lot like a Python dictionary. So you can call the keys method and the values method. The keys method is probably more interesting, so let's check that. Alright, so you can see what keys this object has. What's nice about this is we don't have to use the square bracket notation like a normal Python dictionary. And instead we can just treat these keys just like object attributes. So let's check data. Okay, we can see that it's a big matrix of numbers. This actually refers to the input data that we're going to pass into our machine learning model. Importantly, notice how this big matrix of numbers appears to have no meaning at all. It's just a big table of numbers. What do these numbers mean? Who knows? In fact, the machine learning algorithm doesn't care. All it sees is a table of numbers, and that's all it needs to see. Let's not dwell on this now, but we'll talk more about this crucial point later on. Let's check the shape of this data. Okay, so as expected, it's a two-dimensional array. Specifically, it's 569 by 30. This means we have 569 samples, and each sample has 30 features. Next, let's check the target attribute. Okay, so interesting. It's just a list of zeros and ones. This brings us to another crucial point. Why are the targets 0 and 1 and not another two numbers? Well, in order to truly appreciate why this is useful, you'll have to learn a little bit more about how machine learning algorithms work, so that's something you can look forward to. Generally speaking, if you have k different labels, your labels will be numbered from 0 to k-1 inclusive. Intuitively, we know that we're programming in Python right now, and in Python, array indexes start from 0. Now luckily, the meaning of 0 and 1 here is not lost. We can check the attribute target names, and this will give us the meaning of 0 and 1. So we can see that the 0 and 1 correspond to the labels malignant and benign. And while we're here, we can also check the shape of the targets. Okay, so it's of length 569, just like we talked about previously. Every input sample has a corresponding target. Notice that we can also check the names of the features. So if you were wondering what these 30 features represented, here you go. We can see things like mean radius, mean texture, mean perimeter, mean area. Further down, you can see symmetry error, worst radius, worst texture, and so on. Now, crucially, I want you to notice one important thing, which is that the machine learning algorithm does not in any way make use of these feature names or target names. All it cares about are the numbers. Next, something we like to do usually is split our data into train and test sets. Why do we do this? Well, to understand this, I think a good example is the stock market. Quite intuitively, you'd like to be able to predict the stock market so that you can make money. But of course, I need to be able to predict information from the future, because I can't act on information from the past. So if the stock went up or down last week, I've already lost my opportunity to take advantage of it. But here's the thing. I can't train my model on data from the future, because by definition, it doesn't exist yet. So in order to accurately evaluate my model's performance, I need to make sure that the data I test on is different from the data that I train on. If I test on the same data that I train on, it could simply be that my model has just memorized everything it's seen in the past, which is not useful. That would just be a lookup table, or in other words, a Python dictionary. We don't want to build something that just stores things in memory that we can pull back later. I don't think anyone would agree that this would be considered intelligent behavior, or even learning for that matter. The goal is to be able to predict things I have not seen, not to memorize things I've already seen. So that is why we would like to do a train test split, because we're training on the train data and testing it on the test data. Okay, so let's call this function. So this test size means that 33% of the data is going to be test data, and the other 67% is going to be train data. Next, it's time to build a model. So let's pick the random forest classifier, since that is often a good choice. Now the random forest classifier is an object, not a function. So the first thing we need to do is instantiate it. Okay, now model is an object of type random forest classifier. Next, we call the fit instance method. As discussed, we're going to train it on the train data. Alright, now so far we don't have any feedback for how well this model performs. But luckily, that's what the score function is for. So we can calculate two scores, which if you recall, is the prediction accuracy of the model. So let's print out the train score. Okay, we get 1.0. That means all of our predictions on the train set are perfect. Now let's print out the test score. Okay, we get 96.3%, which is pretty good. So generally speaking, we usually do better on the train set than we do on the test set, but that's not always the case. And now, just for completion's sake, I want to show you how to make predictions using the model. We're going to use xtest here, but you can also pretend that this is brand new data that we have never ever seen before. This is one of the most common questions I get from machine learning beginners. After we train the model, how do we use it to make predictions in the future? Well, this is how. As long as your data is in the same format as before, everything will work as expected. So let's check and see what our predictions look like. Okay, as expected, it's a bunch of zeros and ones. Now, as we discussed earlier, one thing we can do with the predictions is check the accuracy manually. Remember, the accuracy is just the number I got correct, divided by the total number of predictions I made. So let's start by getting n, the number of predictions I made. Okay, so that's n 188. Next, an easy way to count up the number of predictions I got correct is just to use equals equals and then sum over the result. So that's this part of the code you see here. Now this might seem confusing at first, so let's break it down. I encourage you to try out each part on your own if you don't get this right away. So firstly, the equals equals just returns an array, the same size as the originals, of booleans. So you get true if the prediction was the same as y-test and false otherwise. You know what, we can just paste that in here just to see. Okay, so anything we got correct, it shows true. Anything we did not get correct, it shows false. And now we know that in programming, false normally evaluates to 0, and true normally evaluates to 1. Now some languages might complain about what we're doing here, since they are not actually zeros and ones, but Python won't. Of course, if you're in doubt that this works, you can always look at the result and verify that this is the same accuracy that the score function gave us earlier. So let's do that. Okay, 96.3%, as expected. Now, another thing I wanted to do in this lecture was to use a deep learning neural network to solve the same problem. So I've imported MLP classifier from scikit-learn, which is a neural network. And this is something you'll learn about later when you actually learn about deep learning, but we would like to scale the inputs. Alright, so standard scaler works somewhat similarly to a model. We have the fit function and the transform function, and you can do these both at the same time by calling fit transform. So we want to fit on the train data and transform it at the same time, and then transform the test data. So let's do that. We get xtrain2 and xtest2. Alright, now the process is exactly the same. I instantiate my model, which is now an MLP classifier. I call fit. Remember, we want to use xtrain2 for this. And now we would like to evaluate. So we get 99.2% on the train set. And we get 98.4% on the test set. So a neural network still does pretty well on this data set.